Nothing is perfect in this world. Everybody has some imperfections. So is the crystals. So this is the sodium chloride crystals, and if you see, there are some impurities. Correct? So crystals are also not perfect. So one solid has large number of crystals. So defect in crystal happens during crystallization process. So if the crystallization process is very fast, it will become amorphous itself. There won't be any crystals. If it is slow but not that slow, it's moderate slow, there will be some defect. It's very, very slow, then you make it a perfect crystal, but that's very rare, right? Very, very rare. Generally you have some defects, right? So this imperfection in this solids is because of the crystallization speed, actually, and we have discussed that actually, right? So for very good quality of crystallization, of a very good quality of crystals, the crystallization should occur at a very, very slow speed. But even if you do it at very, very slow speed, some defects are bound to occur. And what are these defects? These defects are nothing but irregularity in arrangement. So if you see, there was an arrangement, something else came, some gap came. These are my irregularity in the arrangement. There are two types of defect. One is the point defect, where you have defect at one point. For example, one or two lattice point. For example, in this case, sodium chloride, there's a defect here, there's a defect here. So they have defects or irregularities or deviation from the ideal arrangement around a point, right? Then there's something called line defect. In line defect, we have the whole irregularity or deviation in an entire row of lattice. For example, this is all deviation here. Assuming it has to be all green, there is some red here. Here, assuming it has to be all green and purple, there are some red here. These reds are deviations. So this is point defect. Defects point at only some lattice points. Line defect, defects in the entire row. So we will focus only on the point defects in this chapter, right? So point defects are also of two types. Stoichiometric defects. In stoichiometric defects, we have vacancy defects, interstitial defect, Franklin defects, Schottky defects. We have impurity defect and non-stoichiometric defects. We have these many types of defects. So in stoichiometric defects, actually, the stoichiometry of the substance, the solid, is not impacted. In non-stoichiometric defect, the stoichiometry is impacted. And impurity, we have extra impurity. The foreign elements are there in this. Foreign elements are there. So we'll discuss these type of defects. So we'll start with, in non-stoichiometric defect, we have metal excess defect and metal deficiency defect. So we'll start with this defect now. The first is stoichiometric defect. It's a point defect type, right? And this defect does not disturb the stoichiometry of the solid. Note, this defect does not impact stoichiometry of solid. That means no foreign element in this. So if you see here, there is a gap created, right? This is a defect. There is a gap here. This is a defect, hollow. Correct? So this is the stoichiometric defect. So there are two types of stoichiometric defect. Let's discuss that. The first is the vacancy defect. So in vacancy defect, what happens is some lattice sites are vacant. If you see here, let's assume these are my lattice sites. These are vacant here. Correct? Since some of the sites are vacant, the density is less. This vacancy defect, this will decrease density. Here, some lattice sites are vacant. Correct? It is generally shown by non-ionic, because for ionic there is a complex rule. If plus is missing, there has to be one minus also missing, so that it's neutral, right? The charge has to be neutralized. That's a different story altogether. We'll discuss that. This is generally for non-ionic solids. The next is interstitial defect. So in this what happens is, in this extra interstitial position, right, some atoms come and stay there. So the definition is when the constituent particles, some of the constituent particles occupy the interstitial side. So these are called interstitial side actually. Right, the space in the void in the crystal is called interstitial side. So when some of the constituent particles occupy the interstitial side, it is called interstitial defect. In fact, it will increase the density. Right? See, these are extra. These are extra in the same pack, in the same unit cell. These are extra. It will add mass to the system. Since it adds mass to the system, density is mass by volume. Volume is constant, mass is increasing. That means the density has to increase. It is also by non-ionic only. Correct. So what happens in the case of ionic? So let's see. In case of ionics, ionic must maintain neutrality, because if the compound is not neutral, it will not be stable. It must maintain neutrality. So rather than simple vacancy or interstitial defect here, we have Frankel and Schottky defect. Example is NaCl, if you see Na plus Cl minus, they have this ionic form. So let's see the Frankel defect. So this is a regular arrangement of NaCl, let's suppose, right? I have my Na plus here and Cl minus here. Now what happens is smaller ions are dislocated from the normal sites to interstitial site. Correct? So if you see here, in our case Na plus is smaller, so Na went from here to here. Correct? One more Na went from here to here. Let's see once again. One Na went from its normal position to another place, and one Na also went from normal site to interstitial site. Right? Also called dislocation defect, because there is nothing except but some dislocation happening. Dislocation defect. Nothing is missing, right? The whole system is intact. The number of atoms that should be in a crystal is same. Only thing is they are dislocated. So density is not changed. There is no change in density. And examples are ZnS, AgCl, AgBr, silver bromide, silver chloride, silver iodide. All these show this kind of defect. Correct? And this is generally shown. The criteria was, since the one smaller ions move, so there has to be a difference in the size, right? One has to be a smaller. So difference in size is required here. Difference in ion size favors this kind of defect. The smaller ones dislocate. The next is Schottky defect. Now, Schottky defect, something is missing. But in order to maintain the neutrality, what should happen is the number of cations missing should be equal to the number of anions missing. So if you remove only one negative charge, then the whole crystal becomes positive charge. We don't want that. So one positive charge also should go off. Right? Something like this. You see? Right? One positive and negative went off. This kind of defect is called Schottky defect. And since one cation, one anion in this case, this I showed you, or n number of cations, anions, pairs are removed from this, so density will obviously decrease. Correct? Why? Because density is mass by volume, mass is decreasing, volume is constant for a crystal. Correct? Here NaCl is a good example. And NaCl we have almost one Schottky defect, one defect in 10 to the power 6 ions. that is experimental value. So it is generally shown by a substance which has similar cations and anion size. Cation and anion size. The last defect was not shown by NaCl. This defect is shown by NaCl. Correct. Other examples is potassium chloride, ESCl, AgBr, etc. Please note AgBr shows both defects. This is something special. AgBr is special.